Imagine you're pouring sand through a funnel to build a perfect cone, only to scoop some away and find that as you pour again, subtle ripples form exactly where you disturbed the pile, as if the sand remembers your earlier scoop. This is the Granular Flow Memory Effect, where powders and grains carry the imprint of past forces long after you think they've reset. What is granular memory really? Even when grains flow like a fluid, they jam into force chains, networks of touching particles that bear weight and sculpt the material's response. When you shear, tilt, or compress a pile, you reorganize those chains. Later, under fresh stress, the new flow follows the old highways, revealing hidden scars in the bulk granular texture. How can inanimate grains remember disturbances? Unlike molecules and liquids, macroscopic grains don't thermalize, they stay where you push them. Friction locks them into place, creating anisotropic contact networks. When you reapply pressure, those locked paths bear load first, guiding strain along familiar routes until the system finally rearranges. It's a built-in archival of every past shear and squeeze. But surprising demonstrations exist. In one lab, researchers imprinted letters into a sand layer, then leveled it. Under a new shear, the flow field resurrected the letters faintly in the surface patterns. In rotating drums, granular beds exhibit reversible and irreversible regimes. Small rotations produce identical avalanches back and forth, but beyond a threshold, the pile remolds. And yet subtle echoes of earlier avalanches influence subsequent angles of repose. Why does this matter for engineers and geologists? Because rock slides, silo flows, and pharmaceutical powders all betray their history. A hopper that once jammed in one spot will jam there again unless you fully clear its memory. Earthquake-prone faults remember past tremors in their granular gouge zones, affecting future slips. Understanding memory effects lets you predict where flow will localize or how to reset a granular system. What's the big takeaway for curious beginners? Granular materials aren't simple, dry fluids, but history-dependent media whose present behavior echoes every past disturbance. By studying how contact networks form, break, and reform, we learn to read the hidden diaries of sand and powder. Insights that span from designing better hourglasses to preventing natural disasters and optimizing industrial mixing. Granular materials, sand, powders, grains, exhibit solid and fluid-like behavior depending on applied stress, with flow governed by interparticle contacts rather than thermal motion. When disturbed, they reorganize into force chain networks that bear load along preferred paths, imprinting a structural memory of past deformations. Subsequent flows preferentially follow these reinforced chains, leading to repeatable patterns such as shear bands or avalanches in the same locations. This phenomenon shows that even seemingly random packings retain information about their history, influencing future dynamics. In a rotating drum, partially filled with sand, successive avalanches occur at the same angle and location, reflecting the imprinted failure plane from earlier tumbles. It's like walking repeatedly along a grassy hillside. Each step wears a faint path that guides your next steps along the same trail. Conventional fluids respond only to current forces and boundary conditions, forgetting prior states as molecules mix. Granular flows, by contrast, depend on both present stresses and the way the grains were initially packed, their compaction, and previous shear events. This history dependence means that two identically sheared samples can behave differently if they underwent different preparatory sequences. Recognizing this distinction is crucial for predicting behavior in silos, hoppers, or natural landslides. Two identical sand columns, one gently poured and one vibrated to settle, exhibit different flow rates through the same outlet due to their differing pack densities and contact networks. It's like kneading dough. How you first mix and fold it affects how it will stretch and hold shape later, even under the same rolling pin pressure. Individual grains transmit load through discrete filamentary chains of contacting particles, creating heterogeneous stress maps within the bulk. These force chains form under shear or compression and can buckle or realign under subsequent loading, leaving vestiges of past stress paths. The stability and orientation of these chains determine local yield thresholds and flow channels. As a result, the material's response is a direct function of its evolving microstructure rather than only its instantaneous packing fraction. Photoelastic discs under polarized light reveal bright, load-bearing force chains that persist through unloading and influence where new chains form under reloading. It's like the wooden beams in a building. The arrangement of supporting posts from initial construction determines where the structure will creak or shift under new loading. And at each grain-grain contact, microscopic asperities and thin films lead to static friction that can strengthen over time, a process called contact aging. As contacts age under load, their static friction coefficient increases, making the contact more resistant to slip. This time-dependent strengthening encodes how long a region has been stressed, so that under renewed shear, aged contacts dominate the resistance landscape. It explains why gently loaded sand can lock in place yet liquefy under rapid disturbance if new contacts form. Glass bead packings, under constant confining pressure, show increasing shear resistance over hours, indicating contact aging effects. It's like old leather shoes that mold to your feet over months, providing more resistance to slipping out than freshly broken in pairs. The method of sample preparation, pour, vibration tapping, determines its initial density and anisotropy, or fabric. Dense packings exhibit higher coordination numbers and more interlocking contacts, while loose packings allow easier rearrangements. These differences create distinct memory states. Dense samples resist flow until high shear, whereas loose ones begin flowing at much lower stress. Preparation history thus sets the baseline memory that guides all subsequent flow responses. A vibrated powder bed compacts into a stable lattice that resists penetration by a plunger more than a loosely poured bed, even under the same load. It's like building a snowball. Tightly packed snow holds shape and resists deformation, while loosely gathered snow collapses under the slightest pressure. Granular materials exhibit threshold behavior. They remain rigid below a critical stress and flow above it, creating a yield point that depends on loading history. On unloading, the stress-strain path differs from loading, producing hysteresis loops that reflect internal rearrangements and memory of the maximum stress applied. This hysteretic response can store multiple stress history signatures, manifesting as discrete jumps or smooth loops depending on grain properties. Such nonlinear behavior distinguishes granular memory from simple elastic materials. Cyclic shear in a parallel plate shear cell reveals different torque angle curves for forward and reverse rotations, forming a hysteresis loop. It's like bending a paperclip back and forth. The force required changes with each cycle, and small kinks serve as records of past bends. In silos and hoppers, memory effects lead to flow irregularities like rat hauling or arching, causing blockages that depend on prior discharge events. Predicting and mitigating these issues requires accounting for how past loading cycles have compacted or loosened the material. Similarly, in landslides, the history of rainfall and soil loading sets the susceptibility to sudden failure. Understanding granular memory is therefore vital for reliable design in agriculture, construction, and disaster prevention. A grain silo that emptied once partially will tend to form stable arches at the annular void left by that event, obstructing subsequent discharge until jostled. It's like repeatedly folding a paper fan. Past creases guide future folds, making it easier to close along old lines and harder to open in new directions. Quantifying granular memory demands high simplification imaging, X-ray tomography, or refractive index-matched fluids to track individual grain movements and contact evolution. Discrete element method, DEM, simulations can reproduce history-dependent behavior, but require accurate contact laws and substantial computational resources. Bridging scales from grain-level physics to macroscopic flow remains a major theoretical and experimental hurdle. Progress depends on integrating multi-scale observations with validated computational models. Time-resolved X-ray CT of 3D printed granular packings under cyclic loading reveals persistent void structures that correlate with flow channels. It's like mapping every road and alley in a city to predict traffic patterns. Immensely data unanswerable and necessary for reliable forecasts. Harnessing granular memory, researchers aim to create metamaterials whose mechanical properties can be programmed via controlled loading histories. Such materials could adapt stiffness, permeability, or energy absorption on demand, opening applications from soft robotics to impact protection. Understanding and replicating granular memory mechanisms in engineered composites will drive next-generation smart materials. Ultimately, decoding how sand and powders remember could inspire entirely new classes of adaptive matter. A jammed colloidal gel whose permeability can be tuned by pre-shear cycles, then locked in place for selective filtration applications. It's like training a shape-shifting clay to hold any form you impress upon it, then reconfiguring it by reapplying different pressure patterns.